Good evening, everyone. My name is CHARVI THAKUR from BTECH CSE department from section A2. Today, I'll be presenting on the topic Understanding Quantum Gates Operation with IBM Quantum Lab. The gates I'll be covering including the Hadamard gate, Pauli's gate, CNOT gate, Toffoli gate, and Fredkin gate. So let us begin. I'm starting with the introduction of quantum computing. It is an advanced computational system that operates using principles of quantum mechanics. Unlike classical computing, which use bits that can be 0 or 1, quantum computing uses qubits which can exist in 0, 1, or both simultaneously due to a property known as superposition. Another key property is entanglement, which two or more qubits become interconnected such that the state of one qubit instantly affects the other. These features allow quantum computers to perform certain computations exponentially faster than the classical system. Now let's take a brief overview of quantum gates. In classical computing, the logic gates such as AND, OR, and NOT are used to perform operations on bit. Similarly, in quantum computing, gates are unitary transformation that operates on qubits. So our first gate is the Hadamard gate. The Hadamard gate represent as H, performs a qubit into an equal superposition state. Its operations are defined as H 0 gate is equals to 0 gate plus 1 gate whole divided by root 2, and H 1 gate is equals to 0 gate minus 1 gate whole divided by root 2. This gate is used extensively in algorithms such as Grover's algorithm and Shor's algorithm. It is also the fundamental gate used to create superposition and initiate quantum parallelism. Now, Pauli's gate. Pauli's gate form an important set of single qubit gates. Pauli X gate, equivalent to classical NOR gate, flip 0 gate to 1 gate and 1 gate to 0 gate. Pauli's Y gate performs a rotation around the y-axis, introduce a phase factor along with the bit flip. Pauli's Z gate perform a phase flip, leaves 0 unchanged, but flips the sign of 1 gate. These gates are foundational of controlling and manipulating qubit states. Let's talk about CNOT gate. CNOT gate is also known as control NOT gate. Control NOT gate is a 2-qubit gate. It consists of control qubit, and a target qubit. It operates is as follows. If the control qubit is 1 gate, the target qubit is flipped. If the control qubit is 0 gate, the target qubit remained unchanged. This gate is widely used for generating entanglement, creating Bell states, and implementing multiple qubit operations. Now our next gate is Toffoli gate. Toffoli gate is a 3-qubit gate. It has two control qubits and one target qubits. The target qubit is flipped only when both control qubits are in 1 gate state. It is important because the universal for classical reversible computing. It is used in quantum error correction. It is also forms the basic of many complex quantum circuits. Our next gate is the Fredkin gate. The Fredkin gate is also known as controlled swap gate. It has another 3-qubit gate. It consists of one control bit, a qubit, and two target qubit. The operation is if the control qubit is 1 gate, target qubits are swapped, and if the control qubit is 0 gate, then no swapping occurs. These gate is used in reversible computing, quantum error correction, and energy efficient quantum circuit designs. Now we have to understand about the IBM Quantum Lab. IBM Quantum Lab is a cloud-based platform that allows users to design, simulate, and execute quantum circuits on real quantum hardware. Using the Qiskit library, we can implement these gates easily. For example, from Qiskit import. These gates collectively enable to develop the development of quantum algorithm used in cryptography, optimization problems, quantum simulation, machine learning, chemical and physical modeling, or error correction frameworks. Here are some snapshots of IBM computing platform. We can see the quantum gates and classical gates here, and the measure of that gates also. To conclude, quantum gates such as Hadamard, Pauli, CNOT, Toffoli, and Fredkin plays a crucial role in the function of quantum computers. They allows us to manipulate qubits, build qubit circuits, and understand complex quantum algorithms. With tools like IBM Quantum Labs, we can practically observe and experiment with these gates, bridging the gap between the theoretical and concepts and real quantum hardware. Thank you.